Hi there, I'm Noah, and this is my 5th lab on Faraday's Law. The fundamental principles to this lab are Faraday's Law, magnetic flux, the Biot-Savart law, magnetic force, Newton's second and third laws, and Lenz's law. From the beginning, Faraday's law states that EMF is equal to the negative d flux over dt. And then from this you can take d flux dt is equal to 3/2 mu naught times the magnitude of the magnetic moment times y times magnitude of the velocity times radius squared over quantity radius squared plus y squared to the 5/2. Magnetic flux is flux equaling the integral of b dot n hat with respect to dA. The Biot-Savart law states that b is equal to mu naught over 4 pi times 1 over r to the third times 3 times the dot product of u and r hat times r hat minus mu. The magnetic force is equal to current times delta L cross b, and can also be equal to current times 2 pi r times b sine theta. Newton's second and third laws states that F is equal to ma, and that F net is equal to 0 when there is no acceleration. And Lenz's law states that the induced current's magnetic field will oppose d flux. The details for this lab is that a magnet is dropped down a tube of aluminum foil. My tube of foil was 0.43 meters long, had a 0.023 foil radius and a 0.017 tube radius. My magnet weighed 0.023 kilograms and had a magnetic moment of 2.354 am squared. In my first trial, I got a drop time of 0.87 seconds, second trial was 0.92, third 0.99, fourth 0.93, fifth 0.91, and this averages out to be 0.924. Here you can see the link to my code, and the first part of adding to the code is the geometry of the tube. So there's the length, the width, and the inner radius of the tube, and then the properties of the magnet, so its mass and its magnetic moment. And then the Biot-Savart law is applied to calculate B for a dipole. We then use Faraday's law to be able to calculate d flux at a certain point. And the numerator and denominator both relate to the numerator and denominator in Faraday's law. So, numerator, denominator. We apply Newton's third law to state that the force of gravity on the magnet will be negative mass times gravity, will be the magnetic force on the magnet. And then the F net will equal F magnetic plus F grav. And then to calculate the magnetic force, we utilize our dipole function. We calculate sine of theta, and then we use this to calculate the magnetic force on the ring. And then we sum up all of the ring's magnetic forces, and this will equal the force on the magnet. And so the integral is simulated by using a for loop. And then finally, in the code we have the bar's velocity updating according to Newton's second law, and then the bar's position updating according to Newton's second law. On the right, you can see the final output, with the magnet dropping out of the bottom of the simulated tube of foil, and then the estimated time taking roughly 8 seconds. For the model, we know that red will be clockwise and blue will be counterclockwise, or the induced current. And we know this because the magnet's north will point downwards, and that the induced B is opposing the flux. And then if the magnet ends up being flipped, the colors will swap, but the speed and the position of the bar will end up remaining the same. And the most notable thing here is the significant difference between the computed time and the experimental time, there being a difference of about 7 seconds. And so I believe that this happened because the quality of the magnet that I was using is not good, and that it was also of irregular shape. And when going through my video, the magnet ended up tumbling while falling, meaning that there would be non-constant force throughout it. All of this ultimately causing to not work as it should have, according to the lab. However, the model would be a much more accurate simulation. For the graph, we have a negative slope when the magnet is accelerating downward, so this would be due to the gravitational force. We have a positive slope when the magnet is decelerating, and this would be caused by the magnetic force. And then when the slope is equal to 0, Newton's third law has been achieved, so F net is equal to 0. So what if the resistivity of the tube of aluminum foil was equal to 0? The magnet's flux would approach infinity, as the equation is d flux dt over r. And so this would ultimately mean that the magnet would take longer and longer to fall through the tube. And then if there were holes cut through the tube of foil, there would be a non-constant flux, as every time you approach one of these holes or one of these circles, the force would end up being interrupted. This ultimately meaning that there is less total magnetic force and a faster falling speed. And that's all from me. Thank you for watching my video.